Okay, hello. Today the topic of our lecture would be Boltzmann distribution. And after that, I would be given some basics about statistical physics. Okay. In order to derive Boltzmann distribution, first we would like to consider a gas in a gravity field. So we have a free fall acceleration g, and also due to the presence of gravity, a pressure of gas becomes a function of height or a function of altitude. In order to determine how pressure depends on height, we consider an equilibrium condition for a portion of gas located at a height h. So in order for this portion of gas to be in equilibrium, we need for pressure forces to compensate for gravitation force acting on this portion of gas. So we consider three forces here. First of all is the gravity force mg. I would say not just m, but dm in order to point out that I consider a very small portion of gas. Also, we have a pressure acting from the bottom upwards, P of h multiplied by cross-sectional area of this portion of gas. And there is also a pressure force acting on the top side of this portion of gas, and the force will be equal P of h plus dh multiplied by cross-sectional area of this portion of gas. So the equilibrium condition then writes as P of h a minus P of h plus dh a minus dm g is 0. Then this is a difference between two closely valued functions, and it can be written in terms of a derivative. So it can be written as dp minus dp a equals dmg. And then I write dm as product of density multiplied by volume. And volume I write as a product of cross-sectional area and a thickness of this small portion of gas, dH. And then I multiply it by G. So I have the following equilibrium condition. dP over dH is minus rho G. Then I should express density of gas as a function of pressure, because I am interested in pressure, so I should have some equation which contains only variables related to the initial task, related to finding the dependence of pressure as a function of height. So in order to express a density, I first write ideal gas law, PV equals m over mu multiplied by RT. Then after I divide it by volume, I obtain that pressure is density over mu multiplied by RT, from which I immediately find that density rho is mu p over RT. After that, I make a substitution in the initial equation, so I substitute it here and get minus mu p g over RT. And then I have a simple differential equation which can be solved by means of variable separation. So I collect all unknown values like pressures at one hand side of this equation, while h will be collected in the right hand side of this equation. So I write dp over p is minus mu g h over RT. Then this equation dh here. Then this equation can be easily integrated, and I have finally, after I integrate from 0 to some h, I have the following. I have logarithm of p of h over p of 0 is equal to minus mu g h over RT. Please note that here I assume that this gas is in a state of thermal equilibrium, so I mean that the temperature is constant. Most importantly here is that temperature is not a function of height. So that's why when I do an integration, I assume this temperature as constant. So when I do this integration over h, it doesn't affect, I just simply integrate the h and get h. Okay, at the end I have p of h is equal to p of 0 multiplied by exponent to the power minus mu gh over RT. Well, here we have now something completely thermodynamical, which is at first is unrelated to number density of gas or any kind of a distribution. But now we remember that previously I have derived the following formula, is that pressure in the molecular kinetic theory is given as product of number density and Boltzmann constant Kb and temperature T. So that means that not just pressure declines exponentially with the height, but also the number density of this gas declines exponentially. And next, I somewhat transform this exponential, and instead of molecular mass and universal gas constant, I use mass of a molecule and Boltzmann constant. So I derived both numerator and denominator by Avogadro number. Okay, I should write it in the next line. And this expression can be further transformed into the following one. So now I have a dependence of number density of the gas as a function of height, and as you see, I here have a fraction of potential energy to kBt. Also, please note that number density is related to the probability density in the following manner. Let's assume that we have n molecules, and we are interested in the probability density of a certain molecule to be found in a small volume of space. So let's say this rho of R, and then I multiply it by dx, dy, and dz. So if this is a probability, then the number density in a given point is calculated as so this is an element of volume. So number density eventually is found as dn over dv. So this is total number of molecules n multiplied by probability density function. So that means that from this formula I can immediately infer a so-called Boltzmann distribution. The distribution which allows you to find the probability density of some molecule to be found at any given point of space. Where A here is a normalization constant. If you look closely at Boltzmann's distribution, you will find that it's very similar to Maxwell's distribution. I write here Maxwell's distribution for comparison. So Maxwell's distribution shows you the probability density of some molecule having a speed or a velocity of v. And it's calculated as A multiplied by exponent of minus mv squared over 2kt, kBt. Here again we have a fraction of kinetic energy to thermal energy kBt. Here we have fraction of potential energy to thermal energy kBt. It turns out that both of these probability distributions are part of some greater probability distribution or a more general probability distribution which is called Gibbs distribution. Gibbs distribution describes a probability density to find any dynamical system at any given point of a phase space. So in order to proceed, I first give a definition of a phase space. Phase space is a space which contains both special coordinates of all molecules in gas and also velocities of all molecules in gas. So you can say that if you have n molecules, then your phase space contains 3n special coordinates and 3n momentum coordinates. So instead of velocity, I supplement my phase space by momentum. So momentum represents distribution for velocities. So I can say that I have, for the first molecule, I have x first, y first, z first, and also momentum p first x, p first y, and p first z. And these 6 variables describe me a position of this molecule in the phase space. And also I have other coordinates for all of the other molecules. So for any dynamical system, Gibbs distribution states that the probability density for this dynamical system to occupy a certain point, so let's say some point in a phase space, is some normalization constant A multiplied by exponential of minus total energy of this system divided by kBt. Please note that in the Gibbs distribution, I do not state explicitly whether my molecules or atoms have interaction with each other or don't have. It actually doesn't matter. As long as interaction is not too strong, I can say that this probability distribution is valid. So I have this distribution for a full energy, which includes kinetic energy of molecules, potential energy of molecules, and also an energy of interaction of molecules in between of each other. So I can say that this E can be found as pi squared, as sum of pi squared over 2m, which is the kinetic energy of, this is the kinetic energy of gas, plus I can also add some quantities which are related to the potential energy. So Ui, if there is some kind of external potential acting on our gas. And also, there can be some interaction between molecules. So I can also add a function of over Eg a function which is depending on the relative position of molecules. So remember, please, that when we have studied van der Waals gas, I have introduced a so-called van der Waals potential. So this potential should go here when we study statistics of our van der Waals gas. But if we have an ideal gas, then this probability distribution can be easily decomposed into probability distributions for each of the molecules, as all of these molecules behave independently from each other. So I can write that for the initial system, I have the probability of the system to be found at a certain point of a phase space as and the element of the phase space contains all of the products over all of these coordinates. So I have here and then products over all momenta. But since in the ideal gas we don't have this interaction term, then this probability function can be presented as a product of probability functions related to each of the molecule independently. So everything multiplied by an element of a phase space. So in an element of phase space, I can separate it into elements of phase space related to each of the molecules. So I can express df, d phi as d phi 1, d phi 2, and so on and so forth to d phi n. And here is a typical probability distribution for independent entities. So you can say that if your probability function can be factorized in this manner, that each factor contains only variables related to one independent molecule, then you can say that each of these molecules has its own probability distribution, which can be written as follows. Now again, we have, for a single molecule, we see that this expression can be presented as a product of two probability densities, one of which is related to momentum, while the other probability density is related to potential energy and to special coordinates. So you can say that, again, in an ideal gas, we can consider the motion of molecule, the position of molecule in the coordinate space and in the momentum space independently. And this leads us to Boltzmann and Maxwell distribution. So you see that the Gibbs distribution that I have introduced previously is indeed a more general type of distribution which includes Maxwell and Boltzmann distribution as a simple particular cases which are valid for the ideal gas. So that means that molecules don't have mutual interaction with each other. From this, I would like to start discussions about statistical physics. But before that, I would like to prove Equi-Partition Theorem. Well, previously we have found for the Maxwell distribution that average square of speed is given as from which I can find that average kinetic energy of the molecule actually we can present average kinetic energy of the molecule as follows. And since all of the directions in space are equivalent to each other, we can infer from this that kBt over 2. So that means that if we have one axis and we have one velocity projection here and one component of energy related to this velocity projection, then this average energy contained in this kinetic term equals to kBt over 2. The same is valid also for a potential energy, and the derivation is quite simple. It's similar to that of Maxwell's distribution. Here, let's assume that our molecule is located inside a potential well, and the energy in this potential well is described by the following function, which should be familiar to you, because this function is the potential energy of a spring. So if you have a spring which is deformed, then this is a potential energy for the spring, and alpha being the spring constant. So you can say that there is some kind of an unmoving point, and our molecule is attached by a spring to this unmoving point. Despite that this situation looks quite artificial, actually the result which we will obtain is quite general, as you will see. So let's find an average potential energy of the molecule in this potential well. So here these brackets have the same meaning as I have previously have the same meaning of average as this notation. So it's just two different types of notations for average. And this one is more convenient for me when I have more complicated expressions over which I have to take average. And according to Boltzmann's distribution, the distribution for x coordinate is given by the following formula. Where A is normalization constant, and here instead of normalization constant I can do the following trick as I have used when we have studied Maxwell's distribution. And this type of integral is exactly the same as a type of integral which can be found in any Maxwell's distribution. And please remember about f functions which I have introduced during previous lecture. And this integral can be calculated using these f functions. And the final result is, of course, this potential energy should be equal to kBT over 2. The reason why this potential energy is again equal to kBT over 2, and which is exactly the same as kinetic energy per one axis, is that we have a quadric dependence of our potential energy on x coordinate. So if we have a quadric term in a kinetic or a potential energy of molecules, then this quadric term averages to kBT over 2 of average energy. This allows you to find out the internal energy of an ideal gas. You just write down a mechanical formula which represents a total energy of this ideal gas, and then count the number of quadric terms in it, and then you multiply this number by kBT over 2. So if we have a gas which consists of only one atom, then total energy of this ideal gas is given by summation over molecules of the following expression. Okay, we have 3 quadric terms per one molecule, so I can write that I equals to 3, where I is the so-called number of degrees of freedom. Then average energy, averaged here over Maxwell distribution, will give me I n kBT over 2. So if I have 1 mole of an ideal gas, then this n becomes equal to the Avogadro number. And I can shorten this expression a bit to I RT over 2, where I being equal to 3 gives me 3 RT over 2. So from this expression, I can immediately infer that molar heat capacity of our gas equals to 3R over 2 at a constant volume. If I have two atoms in each molecule of the ideal gas, then I need to add two rotational terms to the energy. I write here the same sum over components of kinetic energy as in the previous expression. And also, for each molecule, I add a sum of 2 rotational terms. If I have a molecule which consists of 2 atoms, with masses m1 and m2, okay, here m is the total mass of a molecule is a sum of masses of each atoms. Then if I have this type of molecule, I also need to include rotation. But rotation can be over any arbitrary axis. And as you know from mechanics, I can introduce 3 primary axes for this construction and express the kinetic energy of rotation as follows. Where G1, G2, and G3 are moments of inertia of this molecule about these 3 primary axes. But I notice that if I take this axis as one of the primary axes, then moment of inertia about this axis is actually 0. So only 2 expressions give a contribution to the total energy. So now I have that average energy per one molecule is 5 kBt over 2, because each molecule has 5 quadratic terms in its energy. Or I can say that number of degrees of freedom is 5. And this leads to a molar heat capacity at constant volume as 5 over 2R. Okay, I can do the similar procedure for 3 and more atomic molecules. And here, when I have more than 2 molecules, I add another one. Let's say I add another one here. And in general, the third molecule is not located on the same axis as first 2 molecules. So we have some kind of a special construction like this. And that means that all of 3 moments of inertia are non-zero, and that means the total number of degrees of freedom for 3 and more atomic molecules is 6. And which gives me the result that CV equals to 3R. Here, I note again that when I have 3 and more atoms in a molecule, then I cannot say that G3 is 0. So I write it, G3 is not 0. And for this reason, and exactly for this reason, I have 6 non-vanishing terms in the total energy of the molecule. So this constitutes a so-called classic theory of heat capacity, which is based on the Equi-Partition Theorem. So in any given system, I find the number of degrees of freedom, I write down the total energy of the system and count the number of quadratic terms in it, and then apply Maxwell and Boltzmann distribution in order to calculate average energy of the system. But for some reasons, classic theory of heat capacity is insufficient to describe real phenomena or real gases. Even ideal gases cannot be described by classical theory of heat capacity. Experimentally, it was determined that actually for any gas, a heat capacity is a function of temperature. For example, for a diatomic gas, molar heat capacity at constant volume may start at 3 over 2R, then increase and at some point reach 5/2r, and then it can increase further. In order to understand the nature of this behavior, we need to consider quantum theory of heat capacity. And quantum theory of heat capacity can be obtained after consideration of the system using the statistical physics approaches. But in order to give you a problem which should be solved using quantum theory of heat capacity, let's consider the following. Let's again consider a diatomic molecule. So a molecule which contains two atoms, two separate atoms. These atoms are combined into a molecule due to the forces which arise when covalent or ionic bond is being formed. So we have some positively charged nuclei of these atoms. We have also electrons, and these electrons form a special configuration which is called covalent bond. And due to the formation of covalent bond, the forces of attraction between these molecules appear, but between two atoms. But these two atoms cannot be found at any arbitrary distance. So when you try to separate these atoms, they attract each other. But when you want to bring these two atoms closer to each other, then they start repulsing each other. So that means that we can assume that these two molecules are connected by a spring. So if we have some kind of a dependence of a potential energy of interaction between these two atoms as a function of distance between them, there is a minimum here at which molecule is found at equilibrium, but if you try to change the distance between two molecules, then the potential energy will increase, and it will not depend whether you go whether you want to bring these two atoms closer or whether you want to bring them apart. And when we have a minimum, then Taylor series for the potential energy can be written as U of R0 plus du over dr at R0 multiplied by R minus R0. And since R0 is a minimum of potential energy, that means that the derivative of potential energy over the distance is 0. So this term is eliminated here. And the next non-vanishing term is the second order term, which contains second order derivative of this potential energy. So altogether, this second term is very similar to the potential energy of a spring. So you have here this quantity as a so-called spring constant. This is effective spring constant, and there is also this quadratic term here. So if I write the energy of this diatomic molecule, I include not only these kinetic energy terms, which were there previously, but also I should include a kinetic and potential energy due to oscillations of this spring. Here, for the kinetic energy of these oscillations, I have introduced effective mass, and here the effective mass is multiplied by squared derivative of separation between atoms, and then derivative over time, which I denote by this dot. So that means that if I consider the spring interatomic forces, then I have another two quadratic terms added into my total energy of the gas. So that means that looking at this expression, actually the molar heat capacity of this gas at a constant volume should be equal to 7/2R. But for some reason, this formula is correct, and this formula works for most of gases, but not this one. Okay, to resolve this difficulty, I first of all introduce concepts of statistical physics. Okay. The main problem which is solved by statistical physics is to find thermodynamic quantities and their fluctuations based on the energy spectrum of the system. So previous expressions which denote kinetic energy of the molecule as a function of its velocities and angular velocities can be considered as a part of this energy spectrum. But on a more general case, all of the systems are described by quantum mechanics. And mostly in quantum mechanics, spectra of systems are discrete. So energy of a system can take only some discrete values, so-called energy levels of the system. So starting from the ground level, whose energy I denote by E0, and then further energy levels E1, E2, and so on and so forth. The continuous spectrum, which is presented by previous formulas, is one of the particular examples of energy spectrum. But for many systems, there are also discrete levels. So first of all, we consider a system which has a discrete energy spectrum. If you want an example of such system, then a simple harmonic oscillator will do. So for a simple harmonic oscillator, we have an energy levels with the following energies. So I here is the number of an energy level, and simple harmonic oscillator is an oscillator which has energy given by the following expression. So we have one-dimensional motion along one of the axes, and this is the spectrum of the system. So quantum mechanics says that if we have a classic oscillator moving along one dimension, then energy of this oscillator cannot be any arbitrary value, but the energy of this oscillator is quantized. And the quantum of energy of oscillator is h omega, where h is Planck constant, and omega is angular frequency. Angular frequency of oscillations of this particular oscillator. Another example of a system which has discrete energy spectrum is a rotating solid state body. So for rotation along one of the axes, the energy is quantized as follows. Here, h is Planck's constant as was introduced previously. G is moment of inertia, and I is any integer number starting from 1. In simple terms, any kind of a finite motion or a motion which happens in a finite volume in space is quantized. So oscillator has oscillations in a finite volume of space because the system cannot reach beyond some coordinate. So it moves in a finite volume of space here. And due to this motion in a finite volume of space, its motion becomes quantized. Rotation also happens in a finite volume of space, and due to this, it also gets quantized, and energy levels are described by this formula. So when we have found an energy spectrum of this system, we want to find out the thermodynamic properties of this system. And the main tool to determine thermodynamic properties of the system is Gibbs distribution. And Gibbs distribution is valid not only for classical physics. Gibbs distribution is a general distribution which is valid for quantum systems too. So main tool to solve the problem stated at the beginning here, finding thermodynamic properties of and quantities and their fluctuations, And the main tool is Gibbs distribution. So the probability of each of these levels, E0, E1, E2, and so forth, to be occupied is a product of some normalization constant multiplied by the exponent containing energy of this particular level and divided by kBt. In statistical physics, typically, instead of this, it's written that this is 1 over z multiplied by exponent minus beta EI, where beta is 1 over kBt, is inverse thermal energy. It's just convention for the statistical physics to denote this normalization constant as 1 over z and introduce this quantity beta. Z has a very special name. Inverse normalization constant is called partition function. And although this that signifies a very simple law that sum over pi should be equal to 1, and that means that z can be found as sum over all energy levels of exponent minus beta pi, the meaning which partition function has is much more than a simple normalization, because partition function becomes actually a quantity which includes all of the statistical properties of the system, and this quantity is sufficient to found all the thermodynamic properties. So if you have a spectrum of the system, if you know spectrum of the system, then you need to calculate partition function z, and then based on this z, you can find any thermodynamic quantity you want. And the procedure is as follows. Okay, let's assume you want to find internal energy if you know partition function z. Internal energy, by definition, is an average energy of the system. So I can write that internal energy, again, by definition of average, is a sum of EI multiplied by the probability of this energy state to be occupied, Pi, and that gives me 1 over z multiplied by sum of Pi multiplied by exponent of minus beta Pi. So this is the internal energy. But we have already restricted ourselves that we only know this function z, and we don't know, and after we calculate this z, we can actually forget about the spectrum of the system. So how do we do? How do we find this sum if we know only z? And it can be done using the by parametric derivative. So let's calculate the derivative of z over parameter beta. So we have z, which is this function, and this is derivative over beta of sum over I exponential minus beta ei. I can take sum out of this derivative, and then calculate the derivative using Chain's law. If you compare this sum with this one, you see that they only differ by the sign. So I can take this sign minus out of here to here. So sum of I ei exponential of minus beta ei is minus dz over d beta. And then I insert this quantity instead of this sum here and get the following formula. 1 over that, 1 over z multiplied by dz over d beta. So I only know in this partition function I find internal energy. Okay. Then you can also calculate heat capacity knowing when you know partition function. Okay, heat capacity at a constant volume. All of these distributions are considered at a constant volume here. So heat capacity at a constant volume is calculated as, okay, this is by definition du over dt at constant volume. So now again I have minus 1 over z dz over d beta. Again calculated the derivative over dt. Okay, I then can again express it using beta quantity. This is actually derivative over d 1 over kb. Okay, 1 over beta. Okay, multiplied by beta. So this gives you heat capacity at a constant volume. And also finally I'll give without a derivation an expression for the free energy. Okay, that is it. So, and also we can, using the thermodynamic identities, we can find also entropy and any other thermodynamic quantities of the system. Okay, as we have a bit of time left for the lecture, or we don't have, how many minutes do we have left? 10 minutes, okay. As we have a bit of time, then I would like to derive a heat capacity of the oscillator. So let's assume that we have some oscillatory degrees of freedom. So by Equi-Partition Theorem, oscillatory degree of freedom, which contains the following term in energy, should give me this amount of energy per one oscillator. Let's check whether it is correct using statistical physics approach. So quantum theory gives you that energies of oscillators can be described by this formula. Where I is an integer value, and omega is angular frequency of oscillations and expressed through the quantities, through the properties of this oscillator as follows. Now let's calculate an equi-partition function. Equi-partition, not a partition function, sorry. So partition function by definition should be equal to the sum over I exponent minus beta E I. There is an additional term, there is a constant term h omega over 2 in each of these energies. And if you take this constant term out of here, it will give you some kind of a constant factor in a partition function. But constant factor will not describe you any kind of thermodynamic quantity. So we can shift all of these energy levels and neglect this additional h omega over 2 term. And then the sum is as follows. We have e to the power minus beta h omega plus e to minus 2 beta h omega plus e minus 3 beta h omega, and so on and so forth. As you see, it's a simple geometric progression, and the sum can be calculated as Or finally we have the following partition function. Okay. From this partition function, we can find an average energy of this oscillator. An average energy of this oscillator as okay, taking a derivative of this function, we get, well, first we write 1 over z. 1 over z gives you e to the power beta h omega minus 1 times the derivative, and derivative gives you minus 1 over e to beta h omega minus 1 squared multiplied by e beta h omega minus 1 and then prime, which means derivative. Okay, minus here with the minus here gives me plus. Okay, this factor here cancels this second power in the denominator, and finally we get h omega multiplied by e to beta h omega divided by e beta h omega minus 1. Then we can write h omega over e to the power minus 1 this 1 minus e to the power minus beta h omega. Or then using that beta is actually 1 over kBt, we can write that the energy is h omega over 1 minus e to the power minus h omega over kBt. As you see, we have something very different from kBt, which we would have expected if classical theory is valid. We have a different expression. And there are two possible limits to this expression, two interesting limiting cases. Of course, not only them, but you can take any kind of relation between t and omega, but two particular cases are of great interest. First case is when h omega is much less than kBt. And then we can write, then in this exponential we have a very small quantity here, and then we can use a Taylor series expression that e to the power minus h omega over kBt is approximately equal to 1 minus h omega over kBt. Then inserting this into this expression, we get for h omega, which is much less than kBt, we have the internal energy equal to h omega over 1 minus h omega over kBt. After we open these brackets, we have at the end h omega over h omega over kBt. Then h omega gets cancelled out and only kBt remains. So you see that when this quantum of energy in oscillator is much less than thermal energy, then that means that we have kind of a classical oscillator. So this oscillator behaves as a classical system. So this equipartition theorem becomes valid. Another case is when h omega is much greater than kBt. Exactly opposite case. You can say that this means that the temperature is quite high. You can say that mostly this happens when temperature is about the room temperature, on the same order as the room temperature. But this is what happens when we cool down system to a very low temperature using cryogenic equipment. And when we have a cryogenic system, then this h omega becomes much greater than kBt. And for this e to the power minus h omega over kBt becomes okay, h omega. So this is something which is a great quantity, and here we have minus. So that means that this should be approximately equal to, okay, there is some kind of mistake. There should be some plus here, but I will check later for this. So this quantity becomes very large, and this internal energy becomes equal to 0. So that's what we should have obtained here. This quantity becomes equal to 0. Okay, here. So this means that this degree of freedom becomes frozen degree of freedom. So when you have a motion in a limited volume in space, we have a quantization. But when this motion is quantized, then when temperature goes below the quantum of energy of this motion, it leads to the freezing of this degree of freedom. Instead of giving kBt as what would happen in a classical system, here we have average energy equal to 0. So this degree of freedom doesn't contribute to the energy of the system. This explains the nature of behavior of heat capacity of any system as a function of temperature. So let's look. So let's look at a plot which I have previously written for the gas. So this is a temperature, this corresponds to a very low temperature. When temperature is lower, the number of degrees of freedom which are frozen is greater. So when temperature of diatomic gas is very low, then rotational motion, the quantum of energy of rotational motion becomes too high compared to the thermal energy, and this rotational motion should not be included in the calculations of heat capacity. At a room temperature and temperatures closer to a room temperature, the rotational motion is unfrozen, and it gives you kBt over 2 contribution for this degree of freedom. But when we increase the temperature further, then it is possible, or might not be possible due to ionization, but if this gas will not get ionized at a very high temperature, then at some temperature it might be possible to reach or to unfroze, to melt down this oscillatory degree of freedom. Oscillatory degree of freedom related to the oscillations of atoms due to interatomic forces. So when we get this degree of freedom unfrozen, then it contributes to a total molar heat capacity. With this, I would like to end this lecture and thank you for your attention.